gesture detection.
Okay, let's get started. So everybody, you can get your exam in that box. And if you have any questions, doubts, or if you want us to regrade your exam, please come to me after the recitation. I'll record your request and let the corresponding TA to grade the exam again. But yeah, if you let us to regrade your exam, you should be very confident that your answer is correct. Your points can actually go down. So just think twice before you make a request. Another thing is we expect you to give us a very brief progress report on your projects. So you should hand in that within a week to email your corresponding TA. I think there's no hard deadline, but you should at least have something to present, or you have some preliminary results, maybe pretty bad results, or some thoughts, or some literature research. But you have to have something to present, and you have to hand in within a week. So we do this because we discovered that like 40% of the groups does not have a baseline yet, or do not have a data set ready. So please, if you do not want to fail your project, please just try hard and do some really focus on your project. So this recitation will be questions on midterm. So basically, I will go over all the questions, and if you have any answers, just if you have any like doubts or questions, just stop me. And so just make sure that after this recitation, you understand everything on the midterm. So it's gonna help for your final actually. So the grade distribution of this exam, the mean is less than 50%. The total score is 82. Since we regrade the last problem, we discovered that the last question is actually pretty easy. It's not what we expected. So actually, Alex changed the questions at the last minute. So so there's some misunderstandings between Alex and TA. So to solve that problem, we just -3 on the total score. So the total score of this exam is 82. And yeah, you probably see that 75 on the exam. So yeah, just ignore that. As you can see, like our math, sometimes our math have problems as well. So somebody gets 68. That's actually pretty surprising. But if you get something like 10 or 14, you should probably work really hard to not fail this course. Okay, so this is a score per question. You can see that students do pretty well on the first 4 questions. And for last 6 questions, problem 8 is okay, since problem 8 is pretty easy. Yeah, problem 10 is also pretty easy as well. I'll go over the graph part in problem 1, and then I'll go over the last 6 problems, since problem 2, 3, 4 are pretty easy actually. Here are TAs in charge of grading. So if you have any problems, like if you want us to request us to regrade your exam, so please find the corresponding TA to regrade the problem. And yeah, you can do that anytime you like. So let's work on the exams. So for the first problem, I'm gonna go over this problem only, because the rest of this problem, you can find all the answers on the slides. So you can just simply copy that from slides. Okay. But for this problem, I actually grade this problem. So most of the people don't get it correct. So most people do not get perfect score. But as long as you draw something, you get some score. So that's the principle of our grading. it's pretty similar to the problem 3, like the break the night base classifier. If you actually write something on problem 3, you get some points. Right? Would be really nice for grading because it's really painful to like see a bunch of zeros. So for the first problem, do you have a eraser or something? So I see a lot of people having trouble with what is true error. Yeah. So you can actually write the sample error as the sample distribution as f sample equals to f true. So we believe that there is some true distribution that we draw sample on, and actually while we are drawing samples, we have to have some errors that we cannot avoid. So the error in sample is actually the true distribution plus some noise. So this is called true error, or called a residue. So this is something that we cannot avoid. So true error means exactly this small residual. So in the training phase, because our model can overfit the data, so actually if you have an extremely complex model, actually you can get an error lower than true error, right? So think about something like if you have, so let's say if you draw some data from a hyperbola, and then you probably draw a point here, and you have some errors, right? So if you use a very complicated model, you can actually have very high order polynomial that go exactly through these points. Yeah, I'm really bad at drawing points. Anyway, something like that. Right? So you can actually have zero error on training data. Right? So this error is smaller than the true error. So if you have a very complicated model, your error can go below than the true error. So we actually covered a classifier in class that can have zero error on training data. Suppose we don't have those like really weird cases like one point lies exactly on the other, and then they have different labels. We don't have that. If we don't have that case, we actually learn a classifier in class that have zero training error. Can anybody remember like which classifier is that?
If you have separability, then at S you have a perceptron
or? We don't assume linear separability.
Okay.
Nearest neighbor?
Yeah. K nearest neighbor. What is number of K? One nearest neighbor, exactly. So if you have one nearest neighbor, we have zero training error, right? So one nearest neighbor is actually the most complicated model in nearest neighbors. If your K grows larger, actually the model gets simpler, right? So if you have infinite nearest neighbor, like it's just like a majority vote. Okay. So that's actually a very nice model for model complexity. A very nice example. So as your model complexity grows, for the training phase you get lower and lower error because your model can overfit. But in the testing phase, actually your error is first going to go down and then go up. Because your model overfits to the training data at the right side of this valley. Right? So at the left side of the valley, it's called underfitting. So I think you probably see the handouts in homework 2 that I wrote about overfitting and underfitting. And you can just go back and check that. So if underfitting case is like if you use a linear model to fit this data, no matter how you place your straight line, it's going to be a pretty bad fitting for all this data. Right? So that means your model is underfitting. Underfitting actually means your model is not powerful enough and the data is pretty complex. Overfitting means your model is over-complex and your data is actually pretty simple. Right. So, yeah, look at this graph. This is actually a very important graph in machine learning. Yeah, do not like just ignore that small crossover on the left side. That's actually some defect for when we generate the curves. There should be just there shouldn't be a crossover. And another problem I see during grading is that people just like reverse this too. Like they get 5K on the top and 100K on the bottom. But that's actually not correct. Because if you have fewer training data, you are more likely to overfit. Suppose you have only one training point or two training data. If you only have 2 points, probably you can use any model to have like 0 error, right? So if you have fewer data, you are more likely to overfit. That's why. So hopefully you all get the points, and I'll go to other problems. I'll probably say like a few sentences for other problems. So for problem 2, this is actually just base rule and some independence, some basic statistics. So if you are suffering from this problem, yeah, good luck. That's all what I can say. So this is actually the most fundamental problem. So if you are not familiar with that, please go back and like take a stats course or something. So for the third problem, as I said, we probably give everybody a lot of points whatever they write down. If they leave blank, we can't give them points, but if you write something, we just give some points. So for the next problem, the perceptron, this is just like you plug in the data into the algorithm, and there's nothing really special about this stuff. If you completely ignore the bias, you can still get the correct answer on the weights. This is actually a defect when we make this problem. But if you completely ignore the bias, you get 2 points off. So, but you can still get the weights correct because the bias are actually pretty small. I think pretty much yeah.
Were we supposed to get it until it converged? Did I make a mistake?
Just one iteration. Just from point 1 to point 8. That's enough. If you get more than that, I didn't deduct any points. If you get like the first 8 steps correct, and that's fine. Right. So I see several copies, like probably 4 or 5, but they just add everything together. So they don't actually check if it is correctly classified or misclassified. They're just adding everything together. Those people get 0 points because they don't actually understand what's a perceptron. But other than that, people get most of them. So for problem 5, the representative theorem. Actually, this is a very easy problem. We did exactly the same thing in class. So I will do that again. Hopefully this time everybody can get it. Yeah, if you are still confused, just go back and watch the lecture video. This is actually like a 2 minutes proof. So, so for this problem, we can actually decompose W. We decompose W as W parallel and W orthogonal. W parallel means W actually in the span of this data set. The span in this data set means W is a linear combination of all data points. That's exactly the answer. W is equal to the sum of alpha I xi. So that means W is a linear combination of all data points, which is equivalent to is in the span of this. So the sum of Wi should not be Wi should not be all zeros. It should be at least some one entry in alpha should not be 0. So that should be that actually is a span of xi. So W perpendicular is actually a null space of matrix X. The null space of matrix X actually means it's perpendicular to every data point. The dot product of W orthogonal is equal to 0 for any data point. So that's actually called a matrix null space. So there's actually a W. There always exists a solution for matrix null space. Anybody?
Zero.
Yeah, all zeros, right? So for matrix null space, there is always a solution. So it's never going to be an empty set. Actually, we can actually go one step deeper. So if I have a data matrix, called this X, and then this is N, and this is F, right? So suppose N is greater than F, and this matrix is full rank. The null space is actually going to be 0. Because since this matrix is full rank, we can select 5 data points that construct act like a basis for F-dimensional space. Right? So we can pick F vectors from here, and then we can construct a vector space of RF. So basically, any vector with length F can be constructed with F vectors in here. So the null space will be all zeros because you can construct any vector with this dimension. Oh, that's the span and null space. So for this dot product term, we can actually decompose that. Since here, W orthogonal is the null space of X, the dot product will be 0. And then that's exactly equals to the dot product of Xi and W parallel. Right.
What about the rest of the problem? Like this minimize only actually deals with the second part of what you're trying to minimize, not the whole expression. Unless I'm missing something.
This one?
Never mind, just let me think and carry on.
Yeah.
You
Okay.
mean the norm of W, the true number of W at the end?
Yeah. Well, no, that's not what I mean, but carry on.
Yeah. So minimize this L2 norm
Yeah.
is you can actually decompose that. Right? So since we want to minimize that, we can completely ignore this one because it doesn't affect the previous one.
Sure.
And you can actually so that actually proves that W is a linear combination of x's. So you probably want to say that you are not minimizing this double parallel. You may have multiple solutions in double parallel, but actually this is enough for proving the answer. So it should be the answer should be a valid subset of W parallel. Right? All W parallel are in the span of data points.
So what happened to the L term, to the last term?
This term?
The last term?
You mean the L2 norm?
No, the loss.
No, in
Curly L.
Some of losses. Loss.
Oh, loss. So actually, now here we're actually proving this this W should be like a a subset of W parallel, right? So since we figure out this W orthogonal does not affect the whole thing, so we just eliminate that. That's it.
And the solution to the original problem.
This is actually the original solution is actually a subset of this. It should be like one W belongs to this W parallel. We just proved that the solution should be some alpha. There exists some alpha that the solution should be in this form.
I guess, so if we factually found what that alpha is
You actually solve this problem.
and solved the problem and didn't get any points,
Yeah, you're not actually figuring out alpha. Actually,
Solve for alpha without knowing the loss function?
you could say it's the derivative of the loss function, whatever that happens to be.
But if it's non.
you have to make
differential-
some assumptions, right, to solve alpha.
All right. Well, it does say it's differentiable. Anyway, I'll ask later.
Alright. So it just says like solution should be in this form. It should be a there exists some alpha, right? So that's
But
that's
what
that's
can
the
you
whole
write?
point.
Minimize the norm of W.
You mean this one?
Yeah.
Since you want to minimize this, so you can actually rewrite the norm of W as the decomposition of this too. Since this one does not affect, so if you want to minimize this term, you can completely eliminate this term, right?
We want to minimize this plus something else, right?
I think the idea is that all this is showing is that whatever the solution is, you can write the solution as, you take W and go, W is this perpendicular and the orthogonal is 0. Sorry, parallel and orthogonal. And so the parallel part is the only part of the solution that will make it through this minimization. And so the solution must be in the span, whatever the solution is. That's what this is claiming.
So you're actually, since the W orthogonal thing does not affect this one, no matter what W orthogonal is, it's not going to affect the loss function.
And
Right.
so we can minimize the L2 norm by making the
Yeah.
orthogonal 0.
Yeah, that's it.
That's because the loss function is an increasing function of.
You don't have to. You actually need to consider about the loss function because this part W orthogonal is not affecting the dot product.
But you're minimizing the loss of the difference, right?
Yeah.
There's a step missing, right? To be able to say.
No. You can the whole thing is that you can decompose this W into this two term, and one term does not affect the first term, the loss
Which
function.
is what? Yeah, why is that?
Because it's the W orthogonal is actually the null space of this matrix, and the null
Yeah, okay.
it means that the dot product with all these terms are 0.
Okay, so you're saying that the inner product of xi and w can be replaced by xi and w parallel.
Parallel, yeah, that's it. Yeah. No matter what this is. That's the representative sphere. Okay, so for problem 6, this is actually a hard problem. Yeah. So I'll just go over how the general solution for deriving a dual form from primal, and then I'll go over the solution. So an optimization problem looks like minimizing some objective function subject to some constraints. So the general process of obtaining the dual form is you first use a Lagrange multiplier, and then put the constraints into the primal form. And then the Lagrange function is maximizing this slack variable and minimizing the original variable with this form. And then subject to alpha is greater than 0. And then you take the derivative with respect to x, and then solve it and plug the x and back to that. So we eliminate all x in this Lagrangian, and then you get a dual formulation. That's a function of alpha. So you maximize over this alpha. So basically, you limit x, so you get a minimize out, and then the only thing left is a function of alpha with respect to alpha is greater than equal to 0. This is actually, if you want to completely understand all these steps, especially why this happens, there is a whole course for that, convex optimization. So basically, why this Lagrangian works is that the dual function of the primal, let's say x star is smaller or equal to Lagrangian x alpha smaller than So this is the primal and this is the dual, and the maximum of dual is equal to the smallest value of the primal, but the optimality holds. So yeah, there's a whole course for that, and actually Jay mentioned this problem in the like 2 recitations ago. So you can check his slides to see. For here, I'll just show you how to apply this to solve this problem. So the first part is actually a small trick. So you can use a slack variable called xi to replace the max term. So we basically let the slack variable xi is equal to the max over I w plus b. That's it. So we use this xi term to replace that, and then we add a constraint on xi. This constraint means for all a's, ai and bi, it should be smaller than that. That actually means xi should be the maximum value of that, all the data points. So this is the first. So this is the first question. Most people made a mistake on the xi term, so you should minimize xi as well. That's a slack variable, you should minimize that as well. So if you don't write xi under the minimize, you get like 1 point off. So the second question is actually deriving the dual form. Oh, okay. That's good. So, so the second problem is solving this to derive the dual form. So we have the original function, and then this is a Lagrangian. You basically add u as the Lagrangian multiplier, and then you maximize over u and minimize over the original variables. Right. And then you take the derivative, set it to 0, and you solve for w and xi. Since you have 2 variables in the original formulation, you have to solve two variables. So for the w, you can derive that w, one derivative is equal to 0. You have w equals to minus a times u. And then you plug that back into the Lagrangian. And then you solve for this xi, and what you get is all the u's must do sum to 1, and that's actually a constraint. So you can, when you solve this the derivative, you can actually get a variable off or get a constraint on the slack variable, on the Lagrangian multiplier. So that's actually yields a constraint. Since u's are all greater than or equal to than 0, so you can write that as the L1 norm of u is equal to 1. And that's actually how you get the dual form. So you can go over this like one time in your entire life and you understand the process. It's actually not that hard if you just go over that by yourself. You can Alex actually go over this for linear programming and quadratic programming in his lecture videos. So you can go and just go over that once if you understand this. It's actually not very hard, but if you work that under time constraint, that's probably an issue. So this is problem 6. So problem 7. If you see the solution, yeah, it's actually not that hard as well. So basically plug in terms. Although it looks pretty scary, so I'll first derive why, I mean, it's already on the slides, so why this derivative of g theta is equal to that form. Alex actually go through this once in the class, so I'll go over that again. So g theta is actually called the log partition function. The partition function is actually like what we said, the normalizing constant. It's very similar to the naive Bayes. Like when we have like PB given A is equal to P A given B. So this term is usually intractable because since P B given A is proportional to this guy, if A is fixed, so we don't usually calculate this PA term, and usually it's intractable. And this is actually the partition function. So g theta is a log of that. So this is written in a continuous form, but that's called a log partition function. So the derivative of that is you simply do the math to take the derivative of log, and then you can discover that the denominator term is actually the exponential of exponent of g theta. So you can just put the denominator to the numerator, and then you have this term times 5x. And this term is p given theta, that's given the problem, and then that's how I derive it. So this is what Alex go over in the class. For the rest, it's simply just plug in all the terms. Yeah, so hx is equal to this one. And then you can replace the log term as the minus of this 2. And then for this term is simply like so for this theta term is actually irrelevant with this integral. So you can actually put the integral over the dot product to the dot product over the integral. And then this term is actually what we derived. This is just a gradient of g theta. And then you do the dot product. For this term, g theta over this guy. This guy is actually the integral of a probability distribution, right? And it should sum to 1. So this term sums to 1, and this term is g theta. That's how I derive the whole thing. So Alex actually go over this one, and that's what I just derived. So you can just go back and check the lecture video, and for the rest of the things they are just plug in terms and do some rearrangement. That's the exponential family. Okay, problem 8. Problem 8 is actually pretty easy. So for problem 1 and 3, I think Alex actually mentioned that in class. So the sum of kernels are still kernel. It does not extend to subtraction. The subtraction does not hold. So sum of kernels are kernels, and product of kernels are kernels. Anyone want me to go over that again? It should be pretty simple. Anyone want me to go over that again? No. Okay. So for the second problem, it's just a Cauchy-Schwarz. You can write the kernel as the dot product, and you square on that. Since use the Cauchy-Schwarz inequality, basically the dot product is smaller or equal to the product of the norms, and then you get the final answer. It's just like 3 steps. Okay, so problem 9. Yeah, this is a hard problem again. So Manzil tells me like he just writing zeros while grading this problem. This is actually a problem on tail bounds. You just have to imagine, like, to just transform this problem to something you already know. So the first problem is actually pretty easy. It's just a uniform distribution. First problem.
What do you mean?
It's just no. If you have one task, what is the probability of like you have m machines, and you want them to have like low balancing? That's just uniform distribution.
But it says regardless of the total number of tasks.
Yeah, that's already in there. It just means like if you have one task.
Intuitively, that makes sense. How do we show it? Because that's what we were asked to do.
If we wrote that answer, would we get the points?
Yeah, I guess if you write uniform distribution, you actually get the points. Basically,
That doesn't show anything, though.
Yeah, I agree with you. Okay. So, let me probably you can argue that if you have, let's say if you have only one task, and you have n machines, so if it follows the uniform distribution, the mean is 1 over n, right?
How do we know that?
You assume that since I mean, if you use other distributions, it's still the same, right? No matter what distribution you use. The expectation does not change. Expectation is still 1 over n. Since that's for an arbitrary, that's for an arbitrary machine, for an arbitrary task. That's 1 over n.
Can you show it somehow?
Yeah. Yeah, probably I'll update this, ask myself to update this. Yeah. It's not on the top of my head, but
Wasn't it?
okay, I'll try to do that later. Thanks. I never thought this would be a problem. So for the second one, it's just a Halberting inequality. So for this one, you can plug in the numbers. So there shouldn't be any doubt on this one, right? If you know Halberting's inequality, so it's minus smaller than epsilon is, I think it should be equal. And then so this is the exponential quantity that's on the right side, and for the left side, if you have the absolute value, it's actually going to be 2 times the exponential, and if it's just the one side, it's going to be just 1. So this is the Halberting's inequality, and if you get rid of these absolute values, it's just going to be half of that, probably.
I don't think the using Hoftings is the problem, it's the setting it up into a form that allows us to use Hoftings that's the problem. I mean, once you have it in the form that you want for Hoftings.
Yeah, since 1 over m is actually the mean,
Okay.
you know 1 over m is the mean, and then it asks that what is the probability of exceeding 1 over m by epsilon, and then there's a hint that use Halberting, so you can simply plug in the mean and the epsilon into Halberting, and you get the answer.
Okay.
Hopefully we're on the same track. So for the third one, it's actually a little bit tricky than previous questions. So the problem asks, what is the probability of none of the machines in the cluster will need to perform more than this fraction of work? So it is equivalent that if there exists 1 minus the probability of, if there exists a machine that exceeds this quantity. Right? So the first step is obvious. This one is for any machine. They are all smaller than this quantity. X is smaller than this quantity. And is equal to, for there exists a machine that exceeds this quantity. And for the second part, you can use the union bound, which gives you the final answer. So the union bound is for let's say you have 2 events, A union B, is smaller than probability of A plus probability of B. You can extend that to arbitrary number of cases, arbitrary number of A's or B's. Since for A union B is actually equal to PA plus PB minus P, they intersect with B. So if you get rid of this term, you can get the inequality. That's the union bound. So the probability here is for one machine, for nth machine, you get that workload more than the mean plus epsilon. And if you use the union bound, it's actually just m times that probability. And that's actually how you bound the solution. That's it.
A question about the previous question with Halberting's inequality.
Okay.
You said the probability that it exceeds 1 over m, but doesn't the inequality tell you that the deviation from 1 over m should be is greater than epsilon is this. So isn't this the union of greater than 1 over m plus epsilon and less than
Yeah,
1
but,
over
but, that,
m plus
but that's actually upper bound, right? You know, no matter what value of epsilon is bounded by that. It might be loose, but that's actually bounded. Right? Because this inequality holds for positive epsilons or negative epsilons.
No, I'm talking about the deviation. It's an absolute value, right? It's
Oh.
absolute value of x minus mu. So it could be either greater
Yeah,
than
like I just said,
oh,
if you have epsilon, if you have an absolute value here, and you are actually smaller than 2 times this exponential. So if you take this out, it's smaller than 1. The probability just decreased by half. That's why you don't have a 2 here. For original inequality, you have 2 times that exponential. So for the second sub problem here, it just asks you that what is the probability of that? What is the probability that is greater than 1 over 1 minus delta? And you can simply just plug in the 1 minus m term into this one and solve for the n. You can simply plug in the term and rearrange it. That's it. So not enough tasks. In this problem, we have m equal to n because we want that infinity thing. So for one task, suppose we have n machines. The probability of this task to be assigned with an arbitrary machine is 1 over n. So let's say the first task to be assigned with the first machine is 1 over n. The probability of the first machine is not assigned with this task is 1 minus this quantity, 1 over n. And then we have n machines, so the probability is just 1 minus 1 over n to the nth. And you can take the limit of n. This is going to be 1 over e. Since you have n machines, the total expectation is going to be n over e. So the last problem. So for the first two questions, just plug in numbers, right? You can copy the inequality from slides and then plug in the mean and the variance. Oh, sorry, this is the older version of the solution. That should be the old one. Okay. So the solution is actually posted on the website in the exam page. You can just check it. So for the first two questions, they're simply plugging numbers, and then you can solve it. So for the third problem, you can argue that since shoes must come in pairs, so you have at least 9 shoes is equivalent as having at least 10 shoes. So if you use 10 here, if you use 10 in the Chebyshev, and then you actually get a tighter bond. That's it. So any questions, comments?
I have that, but on my paper it says a better solution exists.
Yeah, there's actually a post on Piazza
Okay.
written by Dee. Since Alex, like I just said, Alex changed the problem at the last meeting, so we are somehow inconsistent while waiting.
So this question is of 7 points?
Yeah, that's 7 points in total. So if you guys send That's perfect. Okay. I think that's fine with you. So hopefully you're all convinced somehow. And if you have any questions or you want us to rewrite your problem, just take one piece of sticky sheet and then stick that on your exam and write your questions and problems and give us back, and we'll rewrite that.